We continue in this video our discussion about non-deterministic finite automata, and this time we do it on a formal level. So we will define remember our abbreviation NFA. So a non-deterministic finite automaton A is a construct of the following type. This might look familiar to you by thinking about the deterministic automata. So it's a set of states. You have the input alphabet, you have a delta, something about transitions, you have an initial state, and you have a set of final states. And many of these are similar to what we had for deterministic automata. So Q, a finite set of states, just like the deterministic counterpart. Sigma, the input alphabet, finite set. I come back to delta in a moment. Q0 is a state of Q, and it's called the initial state. And F is a subset of Q, and it's the set of final states. So finally, you have here initial, the input alphabet, this is the set of states. And now delta is a transition relation over Q times sigma union with epsilon times Q. It's a finite, obviously, transition relationship. So remember, for deterministic automata, we had a transition function. This time we have a transition relation. And I comment in a moment what's the difference between function and relation in this context. So what this means is that if you have, Q might consist of triples of this form. So you would have a state Q, and you might have a letter here, and you might have a state R here. So what this means, this is really to say that in state Q, or I should rather say from state Q, so from state Q with letter A, we transition, or we switch, we transition to state R. And obviously we might also have for state Q and letter A also a different possibility. This is allowed, and that's essentially the difference between having a function and a relation. If we had a function like we had in the deterministic part, for Q and A there would be a single possibility for what's on the third component. But this is a relation, and it's allowed to have different triplets that differ only in their third position. So that means that from state Q with letter A, we may also transition to state S. And please note that we also have the possibility of taking an epsilon here. So in state Q, we might have an epsilon and a state T. So this might also be in your transition relation. So this would mean in state Q, we may transition to state T, and that is to say without reading anything from the input. So we don't read any letter. In other words, we read the empty word. We read nothing from the input word, and we just we transition from state Q to state T. So this is also allowed in non-deterministic automata. And when it comes to epsilon transitions, so epsilon transitions are all these triplets of this form where we have epsilon on the third component. So these are called epsilon transitions, and by default we consider that we have them defined by default, all these epsilon transitions where we do nothing. We read nothing from the input word, and we don't really change the state. The state stays the same. So these are also included, and we don't have to specify them. They are included by default. And for a letter A in sigma, we have the notion of A transitions. And these are obviously transitions where you have letter A in on the second component. So all these transitions that are telling you with letter A you go from this state to that state, they are called A transitions. And now about reading or doing computations. So I would like to define, if I take an input word W from sigma star, and W is of the form x1, x2, all the way to xn. And this time I'm even allowing the possibility that some of these are epsilon. And they will simply signify how many steps my automaton does, and some of these steps might be epsilon transitions. So if I have such an input word, we are going to define a computation on W in the following way. We will say that if you are in state Q, so in state Q, I just introduce, maybe this is going to simplify my presentation. So in terms of epsilon transitions, I'm just going to introduce this notation. Q goes to T with epsilon. And in case of A transitions, I'm going to introduce this notation. Q goes to T with letter A. So doing a computation on word W, what this means is that you simply just start in Q0, and you go with x1. X1 is either a letter or an epsilon, and you go to a different state, or maybe the same. So you go to a state Q1, then you continue your computation, and you end up in state Q2, and so on. In the end, you get to a state Qn. So this is what this will be a computation on input word W. And we also just denote this by writing Q0 goes to Qn with x1, x2, xn. And we also write sometimes simply Q0 goes to Qn with input word W. What I would like to define is now the notion of accepting or recognizing a word. So we will say that W is accepted, or we also say recognized, by the non-deterministic finite automaton A if Q0 goes with W to some state Q in automaton A for some final state Q. And we also say in this case, so we also say A accepts or recognizes W. And we will say that W in sigma is rejected or not recognized by the non-deterministic automaton A if for all computations from Q0 to whatever state Q is not a final state. So all the computations end up in a non-final state. And so this is the keyword here, accepted or recognized, and in this case is called rejected or not recognized. And we also say about the automaton A accepts or recognizes, and in this case we say that A rejects W or doesn't recognize W. And the language of an automaton, so language non-deterministic automaton A. So this is defined to be L of A consists of all the words in sigma star in such a way that A recognizes or accepts W. And with this concept, we can also define the notion of equivalent automata, just like we had for deterministic automata, so equivalent non-deterministic finite automata. So these are, so A and B, two automata, and they are equivalent, and this is denoted in this way with three horizontal bars. If and only if, that's the definition, the language of A is exactly equal to the language of B. Like we have seen in the previous video, we can also have a graphical representation. So whenever we have an A transition in Q, we can have in a corresponding graph where you have a state for a node for each state P and a node for each state Q. We can have an edge from P to Q with label A, and for any epsilon transition, we can also have an edge from P to Q labeled by epsilon. So this is the graphical representation. And we are going to use this quite a lot when we give examples, so graphical representations. So these are the main concepts I want to introduce, and now I want to give a couple of examples. Here is the first example I want to give. So the first one is I would like to give this automaton. So this has 4 states that I denote by 0, 1, 2, 3. And it has a binary alphabet with 2 letters, A, B. It has a transition relation that I define in a moment. The 0 state is the initial state, and final states, there is only one, and that's the state 3. And delta is defined to be this set of triplets. So I say 0, A, 0, and that means that in state 0, if I read letter A, then I'm going to have as the next state state 0. I have 0, B, 0. We have 0, A, 1, 1, B, 2, 2A3, 3A3, and 3B3. And I can also represent this in a graphical way by saying I have a node for state 0, and I have a node for state 1, and one for node 2, and one for node 3, and 0 was my initial state, 3 was my final state, and then I'm reading from here, it looks like with 0 I stay in, with A I stay in 0, in state 0 with B I also stay in 0, so it's AB, but also I have A is going to switch me from 0 to 1, so I have this transition. With B I go from 1 to 2, with A I go from 2 to 3, and with A I stay in 3, and also with B, so I'm writing A and B. So that's the same way of defining the automaton. So now if I have in the input the word, for example, BA. So the way this automaton computes is I start in state 0, and I'm reading the first letter, and I just check, and it's a B, so the only option I have in state 0 is that I stay in 0 with letter B. And then I read letter A, and I see that there are two options. One is I stay in state 0, and the other one is I go to state 1. So I just indicate this with this branching computation. And then I just develop these separately, or I could even indicate them in parallel. Now I'm reading letter B, and I'm in state 0 on this part of the computation, and with B I stay in 0. And in 1, with B I go to state 2. And then finally I have letter A, and in 0 I either stay in 0 or I go to 1, so I have two options. And in state 2 with A, I go to state 3. And now at the end of the computation, we check 0 is not a final state, so this is a rejecting computation. And 1 is not a final state, so this is also a rejecting computation. But 3 is a final state, and this is an accepting computation. And really, the answer is BA is accepted or recognized. Or I could write BA is in the language automaton A. Now, for example, if I take input, say, AAB. So again, I start in state 0, and with A, I have two options, just like we discussed before. So I either stay in state 0 or I switch to state 1. Then I read letter A, and again, for this part of the computation, I have two options. One is I stayed in state 0, and the other one I switch to 1. And for this part of the computation, reading this second A will just, I don't even have a transition defined, so this is a computation that cannot continue. And with B now, if I stay in state 0, then I continue in state 0, and with B from state 1, I just go to state 2. And that's the end of the computation, and we see that 0 is not a final state, and 2 is not a final state. So these are both rejecting computations. And so the answer is the word AAB is is rejected or not recognized, or I could also just write AAB is not in the language of A. And here is another example. I will define the automaton A to be, so this is our second example. A is made of states 0, 1, 2. And we have again a binary alphabet made of letters A, B, and a transition relation that I define in a moment. And state 0 is the initial state, and final states we have 0 and 2. And the transition relation is made of these triplets, 0A1, 0A2, 1B2, 1 epsilon 0, and 2 epsilon 0. And we can also just show this in a visual way. We have state 0 here, we have state 1, and we have state 2. And we say from 0 I go to 1 with A, and from 0 I go to 2 with A, and then from 1 I go to 2 with B, and from 1 I go to 0 with epsilon, and from 2 I go to 0 with epsilon. And 0 was the initial state, and final states were 0 and 2. And for example, we can calculate on the input word. If we have ABB, we start in state 0, and in state 0 we have transitions with A going to either 1 or 2. So with A I can go to 1 and I can go to 2, and in state 1, if I look at this part of the computation, in state 1 I have two options. One is I go to with epsilon back to 0, or I read letter B. So that's fine. I will consider both of these options. One is I go with epsilon to state 0. And remember, I haven't moved the reading head. So on this part of the computation, I'm still on this letter B. But on this part of the computation, I do read letter B, and I go to state 2. And I hope it's not too confusing for you that I'm showing all of these computations at once. In your lecture notes, you have them written one by one, one under each other. And in state 2, I have the only option is there is no transition with B, so the only option is that I read epsilon, and I go to state 0. And now, on this part of the computation, I'm on input letter B because the moving head hasn't moved, and I should really go somewhere with B, or I should go somewhere with epsilon, but nothing is defined. So this is a computation that cannot continue. And on this part of the computation, I'm on state 2, and I'm with the reading head here on B, and there is no way to continue with B, but I could go to 0 with epsilon. And then in state 0, I'm still on this B, and there is no way to continue either with epsilon or with B. So this is a computation that cannot continue. And on this part of the computation, I'm in state 0, and my reading head is on this B, but there is no B transition from 0, and also there is no epsilon transition in 0. So this also stops. So the answer is all of these are rejecting computations, meaning that ABB is not in the language of A. And as a matter of fact, We don't have the tools in this lecture to calculate the language of this automaton, but we will have them in a couple of lectures. And I can just anticipate and announce that the language of this automaton is in fact exactly the same as the language of this regular expression, which is A plus AB star. And finally, I want to give just one more example, and I'm going to show it on this part of the whiteboard. And this example is, I will take the automaton B to be, again, 3 states and a binary alphabet. And I have a different than this delta, different transition relation that I will show in a moment. And initial state is 0 and final states are 0 and 1. And this delta prime consists of transitions 0A1, 1A0, and 1B0. And so as a graphical representation, what I have is that I have state 0, which is an initial state, and I have a transition from 0 to 1 with A, and from 1 I go to 0 with transition A. And as a matter of fact, I also go with transition B. And state 2 is somewhere here, and the final states are 0 and 1. And obviously state 2 is unreachable from 0, so in that sense it's not even needed in the definition. But because it was specified here, I'm going to show it as a separate state. And the only point that I want to make, but again, we don't have the tools in this lecture to check this result, but we will have them in just a couple of lectures. I just want to anticipate that, in fact, the language of the automaton B is exactly the same as the language of the automaton A. So, in other words, B and A, they are equivalent.